In this very important video, I'm going to introduce the idea of combined concept problems, which are a huge part of University Physics 1. What I mean by combined concept problems is that they're problems that don't fit into a single category of, say, constant acceleration motion or non-constant acceleration motion. Or eventually we're going to have it where maybe you have a problem that has 5 steps. So first you have a one-dimensional constant acceleration motion, but then you need to use Newton's laws, and then you use conservation of energy, and then you use conservation of linear momentum, or something like that in order to get to a final result. So identifying what concept applies to each part of a problem is a critical learning skill that we are focusing on throughout this course. And in 1D motion, we've really only learned about one-dimensional motion, but we do have 2 types of it. We do have our constant acceleration motion, which we can use our nice little kinematics equations for. And then we also have our non-constant acceleration motion, which we have to use calculus for. So as an example, our first example of a combined concept problem is that you'll encounter is that when you have to do part of the problem using calculus, and then a second part of the problem using the kinematics equations and the constant acceleration equations. So in general, it's going to become required starting with week 2 that every problem you submit, you have labeled the concept that you're applying at every step of a problem. So far, like I said, we have 2 concepts. So far we have constant acceleration in 1 dimension. And then we also have non-constant acceleration in 1 dimension. And the reason it's important to be able to name these is because if you know the name of the concept you're applying, each concept comes with its own toolbox of how to go about starting those problems. So for combined concept problems, for the portion that involves calculus, that involves the non-constant acceleration, then you know that you're going to want to use calculus in order to be able to solve that. So you would want to be able to use a derivative or an integral and kind of get to where you need to be. So you have a starting point, and that's really important so that you don't get stuck wondering how to even start a problem. So identifying the concept is huge. If it's non-constant acceleration, use calculus for that portion of the problem. If it's constant acceleration motion, then you can use one of the 4 kinematics equations. So I just call those the kinematics equations from the video on constant acceleration motion. So an example of this, and one that you'll work through, is let's just say when you throw something up in the air, a lot of times we just analyze the motion after it leaves your hand, in which case it's only being acted on by gravity and it has constant acceleration motion. But in real life, we actually don't want to ignore the time that it's in the hand. So there'd be some acceleration in the hand, which depends on time, right? So there might be some variable time constant acceleration or time dependent acceleration in my hand. And then that gives it some velocity. And then that velocity is the initial velocity it has for the free fall portion of its motion. So as an example, if you throw a ball upward, and let's say the acceleration in the hand varies with time. So, maybe you have this sort of portion where it's in your hand. And so the ball heads upward, and then after that, it goes up and then it comes down. So this would be when it's in the air. How you would solve this problem is you would apply 2 different concepts to this. Here, you would use calculus, and then here, you would use one of the kinematics equations. And when you solve it, you would just label it as non-constant acceleration, and then you write out the calculus parts, and then you write constant acceleration motion, and you write your kinematics. As we get further in the course, we'll have constant and non-constant acceleration in 2D, and then we'll have Newton's laws, We'll have circular motion, then we'll have conservation of energy, conservation of momentum, and then we go back and do that whole thing in rotating systems again. So we're just at the tip of the iceberg here in terms of what combined concept problems will have to offer us throughout this course. All right, let me know if you have any questions.